Okay, tonight's speaker is Dr. Saw Hla from the Department of Physics and Astronomy, and he's going to talk to you about how you get soccer and molecules in the same sentence. So, with no further ado, Saw?
Okay, so thank you for a nice introduction. And well, the title already explains something, right? So it's nanoscience. This is what I'm going to explain a little bit. And of course, playing with soccer with atoms and molecules. So I understand that this is for a general audience, and please ask questions to me. That's why I'm here. So let me start with who I am just before I explain things. I've been here in Ohio for 13 years as a faculty of physics. That's what I used to teach my classes, undergrad classes. And since 2011, I also took a joint appointment with Argonne National Laboratory. That's the US government lab. It's from US Department of Energy, and I'm head of a nanoscience group in this laboratory, and this is one of the largest, well, not one, the largest light source in North America. This is where my lab is located now in Chicago area. And this is about 1.1 kilometer in circumference, and it produces about 9 giga-electron volt energy of the X-ray beam. But today what I'm going to talk about is about the atoms, not about this. And after my talk, after my discussions, I want you to ask me any questions, anything about nanoscience, I will try to answer it. So let me start this way. First, we need to know what is nano. Okay, I'm sure many people already know, but if you don't know, let's see about this. So 1 meter is, I forgot to bring a meter stick, but it's about this size. Approximately, it's about 1 yard, okay? That's called 1 meter. Nano means if we divide that 1 meter 1 billion times, 1 meter divided by 1 billion. So nano is 1 billion times smaller than a yard, approximately, about 1 meter. Okay, so it's very, very, very small. So this is a 1 nanometer is 1 billion times smaller than 1 meter. That's fine. Now, what is the atoms? Well, everything that you see, including yourself, the building, the universe, are all made of atoms. Okay, so we are made of molecules, the proteins, and whatever the cells. If you look at the cells, you find there are small molecules of DNA, and in DNA you will find those things are made of atoms. So the atoms are, you can say it's a basic building blocks of us and nature around us. So now, before I continue how to play with the atoms, let me establish the size, just for you to understand, okay? So, you see that little dot? Suppose this is the atom. The actual size is about 1 billion times smaller than what you see in this, the screen, the projection. Now, that's me, a little different dress during the convocation. Let's do this way. It's better this way. Oops. Okay, that's a little better. Because I'm going to enlarge myself to 5 million times. If I enlarge myself, my height, 5 million times, I will be the length of United States from east to the west coast, approximately. Okay. And if I enlarge that little atom 5 million times, we will get to the size of about an ant. So that's how small an atom is, just to see. Now, we want to play with the atoms. Remember, we, as a human, size will be like America size, is going to play with a small ant. That's what I'm going to show you. And not only that, we can actually control where do we want to be. even half of this ant size with that size of America, like ourselves. Now, the first thing we need to know, if you want to play soccer or forget about soccer, anything you want to play, the first thing you need to know is you must see them. If you don't see the atoms, how can you play with those atoms? So we need to know, how do we see things around us, right? You see me because of the light. The light, if we turn off the light, you don't see me. So how do we see things? That's just very simple. There is a light source somewhere, and that light hits to the objects, including us, and then reflection enter to your eyes or my eyes. And I can see you, you can see me. So if we want to see the atoms, then we have to use some form of the light. But can we do that? Well, let's see this way. The light, as we know, the white light has different colors. If you combine those colors, you get a white light. The colors of the rainbow, that's well known. Okay? And the light is formed by a small wave packets called photons. And the smallest of this is, you don't even see it, it's very dark here. This is about 400 nanometer. So it's like following things. I just think this way. If you want to measure something, let's say your watch has up to the millisecond you can measure, but you can measure microseconds because it's so small, so fast, I'm sorry. You can measure it. The same thing, the atom size is 400 nanometer, but the size of atom is about 0.4 or 0.3 nanometer. So it's not possible to see with the light. Size of an atom, let's call it about 0.4 nanometer. Okay, so actually that's a larger size. Atom size could be 0.1 to 0.4. Then you will notice that the wavelength of a smallest light, visible light I'm talking about, is at least 1,000 times larger. So the atom is 1,000 times smaller, so you can see with the light. I have actually drawn an atom. I don't know whether you see it, little dot here. That's the wave packets, the wavelength. That little dot is the size of the atom, so you can see with the light. Okay, so that I just enlarge it. So now, the things that we use to see small things called microscopes is microscopes, normal optical microscopes are useless. We cannot use to see the atoms. If you can see the atoms, you can play with them. Forget about it. So, first thing we need to establish is we must see the atoms. So that's, I will start with my discussion today. I'm going to show the demonstrations, and then I'm going to tell you and show you how do we play soccer with the atoms. So, but we were lucky because of these scientists, physicists. These two guys, these two gentlemen have invented a new type of microscope. It doesn't use light at all. This is called scanning tunneling microscope, and they got Nobel Prize in 1987, sorry. And this invention led us to see the atoms. So how do we see the atom? I'm going to demonstrate. This microscope doesn't use light. It uses very sharp needle, and that needle is called the tip. Here is the cartoon I'm showing, okay, but I will show you exactly what it does. Okay, so this is handmade, but every object is formed by atoms. So the sharpest one that you can see at the end should be one atom. Okay. Now, I don't know whether you can see this one. It's a little high for you maybe. This is, suppose that these are the atoms. Okay, so this is on the surface. If we want to see it, what we do is we use this very sharp needle and approach very close to the distance, and you sense it. And if you are very close and you gradually move, you will see that now this one is moving along a profile of the atoms on the surface. It's just moving along the profile. And the movement of this profile, we can record it with the computer so that we can see the profile line by line. Okay, I'm going to show this again with little movie. And now this little tip is moving, and it's called scanning. It's moved along the profile of these atoms on the surface. So we are sensing it. We don't use light. Now you have a single line of this, and those lines, if you stack in the two-dimensional area, okay, an area, you get an image of atoms. For example, here, these are individual atoms that we can now see through this way, this technique. So this is a very important technique. It requires that the tip, we call it, has to be atomically sharp. Of course, we don't know whether it's atomically sharp, so we have to test. For example, the other end of this, my demonstration, this tube, is not sharp as compared to this one. Then I cannot get the profile of these atoms. Because this is flat, I will get only a straight line. Only at this size, it can enter to the atoms. I can show you here. You will see that how it goes. Then you will get the profile of the atoms if you do this way. Okay? So that's how we do. So what I'm going to show you now is, before I continue my discussion, I have, well, not I, but my students have made, Saito has made 6 tips. It's made of the tungsten wire. And we are going to show you around. So, Jordan, could you please? So it has a magnifying glass, and then there is a tip, and you can open this little capsule, but don't touch inside. It's dangerous. It's very sharp. Okay, and then you watch this with the magnifying glass. Try to see the tip apex. It's a very important. That's the tool I'm going to use to play soccer. Okay, not only to image. And I'm going to show a lot of different exciting things to you. Okay, so please to pass around. So now you understand one thing. This is called tip. It's a needle, and we sense it. Okay, so we sense it along the profile of the atomic profile, and we can get images by the computer. We can see the atoms without light. Okay. Now, before I continue this presentation, I want to bring you to a movie. Let me see. I want to show you a little movie to visit the atomic world. Okay, so. Okay, now let's have a look at it. What you see here are these individual dots. It's written as a Q, it's letter Q. Each one is one atom. And the background you see like wave-like things, those things are electrons. In this small scale, we can see electrons like water. Okay? Electrons are no longer a particle. It's called quantum mechanics. So here, like a little pool, what you see inside is the water, or in this case, electrons, cannot go out, so that it's like ripples formed. These are electron waves called standing waves. And this is a beautiful phenomena which we are going to apply in nanoscience for the humankind. I'm going to explain later point. So now let's go and visit to the atomic world. Consider yourself sitting in a kind of a space shuttle vehicle, but we are not going to the space. We are going to the very small scale, the atomic world, and let's go and visit. Let's go and see the atoms up close and personal. Now, let's see how things work. All right, this is the real image, okay? It's not a fake. It's not a drawing. So now we are going to go in and have a look at it very close up to the atoms, okay? So now you see those are the atoms. These are the electron waves. You can see very clearly the waves. And this is how the electrons looks like. Okay, so I need to stop here. Sorry. So we crashed, but it's fine. We still survive. All right. So now you are you are looking the tips. I'm hopefully passing around. It's already okay. Why don't you just give it to the back as well? And I want to explain a little more detail about this tip. Okay. So this is a tip that we use to image the atoms, and an example tip, of course. And let's have a look at the size of this tip, right? So at the apex, you may see it in the light with magnifying glass. It looks pretty sharp. And this is about 300 micrometer. Micro is 1 million times smaller than 1 meter. Okay, 300 micrometer. And that's about 0.3 millimeter. Okay? And this is about 100 micrometer. Let's compare this tip with the Eiffel Tower, right? Just for the sake of understanding. And Eiffel Tower turns out to be the same ratio, but 300 meter, that is about 300 yards tall, and 100 meter wide. Okay? So it's like the same ratio. But if you divide 300 meter with 300 micrometer, you will realize that Eiffel Tower is 1 million times larger than the tip that you are looking at now. So little tip that you are looking at, if you enlarge this to 1 million times, you will get the size of the Eiffel Tower. Okay? So when we take the images of the atoms, I told you already, we have to be very close. Actually, we have to be close less than 1 nanometer distance from the surface. Only then you can sense these atomic profile. So if we use simple ratio, if we multiply 1 nanometer 1 million times, then what we are doing in STM is very simple. It's like we are using Eiffel Tower, okay, to image the ground from 1 millimeter distance, and we are moving this with 0.001 millimeter steps. Okay, so that's the control that we can achieve nowadays. That's why we can see the atoms. All right, so I want to show one more picture. So the instrument that we used here was a home built. It was built 12 years ago. I'm very proud of this because in this picture, what you see, these young boys, they were Ohio students, and we built it here at home. And these students, for example, Kenneth Clark now is a Professor Kenneth Clark at the Missouri University. Joe Vaughn, he was an undergrad student, honors tutorial student, and he is now Dr. Joe Vaughn. Danda Achaya, he was my grad student, is now Dr. Achaya. He's now at the scientist in New York at Albany. And Thivo is an instructor in the second largest robotic companies in the world. So those were Ohio students and built in Ohio University. At the time of this instrument that we built, we were the first instrument of this kind to play the soccer well. I will see not just the soccer, in entire Midwest and even to the East Coast. There were only one at the West Coast. It was an IBM in California. So we were the first lab in this side of the world to achieve this level at that time. That's why all my students been very successful. Now, okay, I have already mentioned about how to see the atoms. Now we can see the atoms. How do we play soccer with the atoms? Okay, so in order to play the soccer, of course, you need to have a few things, okay? So if you want to play the soccer, you have to control the balls, right? You have to be able to stop the ball, soccer ball. You have to be able to kick the ball to the place that you want to go. What I'm going to show you today is, of course, playing soccer without opposing team. So it's like alone that I'm playing myself, but we can play. So the way we do it is, again, I will show you here with this little movie. So we use that little tip to kick the atom. The atom moves in step-by-step manner. It's not continuous. It's discontinuous. You will see that it's move, stop, and move. Okay. So this movement, we can listen the sound. I'm going to play the sound. Let's hope this works. Listen. These thump thump are jumping sound of the atom. Okay? So we can listen this also by recording the same signal with the tip. So we use the tip not just to image but to play the atoms. So here is a moving of a little one atom with little green color, and that's what we are control. We control this to move around. It's like we are playing with little soccer ball. Okay, so all right. So what do we do with this? The first thing, of course, being at Ohio University, is well, we want to write OU logo. So what you see here, little white dots are individual atoms. Each white dot is one atom made of silver. The background, the blue color, is also silver crystal. Okay, so and you will see this is the real construction. It's not a cartoon, and so we move these atoms to write the letter O and U. You will notice that after writing O, there are waves form inside. You understand what these waves are now? Because they are basically the electron waves. Okay? Now, this, of course, not only this U, but also we have built this little heart shape by moving the atoms, and then we decorate it further. So now I'm going to demonstrate how we move the atoms with these little balls. Okay, so this is the ball shape. Assume that this is atoms on the surface. Okay, so how do we position these atoms with this tip? You have already seen that we can image the profile of the surface with the tip. Now I'm going to use the same thing. I'm going to kick the atoms like this. That's where the sound that you heard, because these atoms jump one step, it makes one thump, right? Now, of course, you have to know where you are positioning, so you need to be precisely control this. I'm controlling this precisely. This, what I'm showing you, is exactly what we are doing in 1 billion times smaller scale, very precisely. That's why we can write these logos with atomic scale. Otherwise, we cannot. So now I'm just positioning this one. I want to build a little row of the atoms. Okay. Now you have to see the atoms, and you have to feel it, and you have to push it with the tip. Okay. So we control this movement. Right now I'm controlling with my hand. In reality, we control this with computer. Okay. So I need to bring another atom. Now you will notice that I have to bring in a certain direction because the surface is not flat. And because of these little bumps here, but that's what exactly at the atomic world, because that's the surface is made of the atoms itself, so that they are not flat, and they appear to be flat, but they are a little bit of corrugations. Those are made of the atoms, the atomic corrugation. You have to overcome these corrugations, so you need some force. And we can actually measure how much force need to move one atom to one atomic size. And I can tell you this. This is about 12 piconewton force to move one atom. Okay. So now I'm trying to build this, the row of the atoms, and that's what we actually do in here. At this, you see that there is an atomic row. I have built it one. Just go ahead, please.
To create each frame of that video, you have to take the time to scan that sort of
Exactly.
area, right?
Exactly.
It takes a while.
Exactly.
So that's the way to think of this. Every one of those frames, you had to scan to create. Then move one atom.
Exactly.
Scan the whole thing, that's your next one.
So the question is following. During this movement, we have to move, and then after moving, we have to take image, a frame. Only then I can show you a movie by stacking these frames. So it takes some time. So let me explain this way. We move one atom. I will show you again. Okay. So here you see as a continuous. In reality, we stop here, for example. We stop the point, we take the image, and then we move the next atom, and then we take the image. So, of course, we have to. Otherwise, we are using the same tip to move as well as to image. You can get both at the same time. So yes, we take the image of this, and then the next step, we move the atom. Thank you for pointing this out. And we take another image again, and we move another atom. Okay? And so that we know that we have moved the atom, so we can see that the atoms are forming a line, and then, of course, we can build the structures. So in relation with this, let me explain how long it takes to build this. This particular logo takes 26 hours. Okay. So, but of course, I can build it in about 100 milliseconds if I want to, but I cannot show you this beautiful movie. Then I can move all the atom at once, and because the scanning speed can go down to the milliseconds, so that we need only a single line to move an atom. So we can build it in maybe a few seconds for entire thing. Okay, but can be faster than this. Okay, so now this is the three-dimensional image. You can clearly see the atoms here, and you see again waves. These are electron waves. This is a real logo of Ohio University. It's about 30 nanometer wide. And remember, we can write about 200,000 of these logos in the cross-section of your hair. Okay, just to get the idea, right? Cross-section of your hair, we can put 200,000 of those. Okay, so that's the smallest logo in the world. Okay, so where do we go this with moving atoms? Of course, I'm here at the university as an educator. Of course, we want to also show this to the kids. This is the high technology, okay? We are at the control at the atomic scale. We built our own machine, and we demonstrated that we can control it. But not only us and my students, we reach to the kids. Now I'm going to show you about the kids and how they move the atoms. So this was in 2009 in Physics Open House, and that's normally we do every year. And so we invited the kids. They visited to us at the lab. And at the left side, at the picture where the kids, I don't know if you can clearly see. Can you a little bit reduce the light, please? Can you reduce the light? Thank you. So here are the pictures of these little kids. And these kids were in my lab, and these were my grad students. Heath is sitting there. And they are helping the kids to move. And their task, their mission was very simple, to write this little school bus. Here is a drawing. And this drawing has to be, little dot here are the atoms. So their mission was to build little school bus, namely the world's smallest school bus. Okay, I'm going to show you a movie here, and that's actually were built by kids. Each kid moved one atom, and that's how we made this movie. You will see that these little dots, that's moved by the kids up to 12 years old. Okay, so now that's the little school bus, right? This is the world's smallest school bus. And of course, 3 years was held by the mother. She's also my grad student. So, but nevertheless, we have this little school bus. Okay, so it's nice to show these little writing things. And of course, we are demonstrating our control at the atomic scale. But can we apply these things? Can we use something useful? Well, the first thing I'm going to show you is another fancy thing. I name it, it's Nanogun. Okay, so the first thing I'm going to put, why I call Nanogun, I will explain it. So in this case, we want to build a little structure where we can shoot the molecules. It's like a bullets, very precisely and very fast, but at the nanoscale. So here you will see the movie showing construction of this structure I'm sorry. So this is the, what you see here, this area, this is, we call it the cluster. This is little piece of silver. It has probably about 100 atoms inside. These are individual atoms, okay? So we are going to pull out the atoms from this, also with the STM tip, and then we move the atoms to position two lines. And you will notice that electron waves appear straight after this. Okay, so we use this. We use these electron, this as a track to shoot the molecules. So we have here molecule, this we call it molecular bullets, sexy-phenyl. Here are our targets, are two atoms. They are exactly at the in line with this, okay? And so we again kick the molecule with the tip from the back, and these guys move, and it should hit the atoms. So here it is, again, the same one, different color, and we shoot that one at the up one, and after hitting this, it bounces back. This atom is gone because it's combined with here. This one is on its way to this. Okay. So we can shoot very precisely at the atomic scale, and we compare this with the gun, right? So the speed we measure, we calculated it actually. I won't go detail. Appear that the speed of this is equivalent to 60 miles per second, and if you compare with the fastest rifle, if you are NRA, I don't know, you will know that it's about 1 mile per second. Okay, so compared to the rifle, we are basically 16 times faster than the bullets. So this is basically the fastest and the most precise gun in the world. It works only at the nanoscale. Okay. Now, what I'm going to explain from this point on is we are going to use this technique, this wonderful technique, to learn about our nature. So, and this is actually what the research that in my lab at Ohio University is doing, and also part of it what I'm doing in Argonne National Lab. And so the first thing I want to explain is, okay, we have this wonderful technique. We can image, we can kick the atoms, we can position very precisely. So what are we going to do with this? Of course, we want to apply this in nature. So this project started with one of my undergrad students, 2003, Jessica Benson. She came to my lab and told me that she wanted to use this, kicking the atoms, to chlorophyll. So I said, what is chlorophyll, Jessie? She said, you don't know that? I don't know, I'm a physicist. And she's, you know the fall color and during the fall time? Yes, it's beautiful in Athens. I remember. It's red, yellow, green. And she said, it's because of chlorophyll that produces green light and it's dye. I said, okay, I don't know what dye mean, but it's fine, let's play with that. So let me explain what is this. Chlorophyll is the molecule that makes the plant leaves green color, okay? So when the light, which has a white light, has all the colors, a rainbow color, I already explained. When that falls into the plant leaves, it absorbs all of them except the green. It cannot absorb, so it throws back. But we see things when the light enters to our eyes, so only green is thrown back, so we see the green. That's why we see the green color. That's the molecule. Here is the structure. You don't have to understand too much. If you're a chemist, you understand. Otherwise, biologist, you will. Otherwise, just forget it. But I want to show this, that there has a one big blob and there's a long chain here. And this molecule is also very important for our life because that produces oxygen that we breathe. It's called photosynthesis. We won't be here today or any life form on the earth without these plants and these molecules called chlorophyll. But nobody have ever seen this chlorophyll at that time. People draw cartoons like this, okay? But show the image, the photo of this one. Nobody can show this. But we can see the atoms, so why not we take the image of this? So we did, and this is the chemical structure. Just forget it. Here is how it looks like. Now it is in a textbook, in biology or plant biology textbook. I have given the permission to print, and this is how it looks like. the molecules, we have the tail. This is called tail, long chain, and there's a head, and that's how a one chlorophyll molecule looks like. Now, what do we do with this? We can not only kick around the atoms, but another thing that we can do with this tip, it's very useful, is that we can position on the top, we can apply the electric field directly to the atoms or molecule underneath. We can give the energy at a very specific position, okay, so that we can change by applying the energy. So what we did here is we applied that energy to this location called A, and we inject the electrons. By doing so, we can change shape of the molecules like this, okay, and we can do it in a controlled way. And then I will show you in a minute. And we inject another area called B, we can change another shape, and we inject this again, we can change another shape. So in chemistry, it's called conformation, okay? But layman term, the shape. It's like you are sitting, you are standing up. It's the same you, but two different form, okay? Here is 4. So what we did at that time was we changed this continuously, and I'm going to show you with a little movie, and let's see. Here, you can see that we can repeatedly change. Again, the same thing, we change the position, we take the image, and we change it again, and we take the image. So, and then we stack the images, animate to show this movie. And this movie was in 2007 in Paris fashion show with catwalk. They said it was a nano catwalk. So in the background with this, and just imagine, now you see me, I'm sorry, but it was, the catwalk with beautiful ladies, and the background was this. Okay, now we want to apply this to another useful area. That's in biology, okay? So, all right, so this is what we are interested in, Alzheimer's disease. I'm started to forgetting things. I'm starting to worry that I may get Alzheimer. Anyway, so that's one of the motivation, that maybe we should study this. And nobody has used this technique in biology. But we can see the atoms. Why not the molecules? Why not the proteins? So let me talk a little bit about Alzheimer's disease. Here I borrow from the web. Here is the slices of 2 brains. The right side is a normal brain. You see the full. The left side is Alzheimer's disease. People who has Alzheimer's disease has a smaller brain because part of brain slowly die out, so that you start to forget things if you are getting older. Now, why this has happened? Well, this is how it explained. There is a protein, a precursor protein called amyloid precursor protein, and those pieces here in the drawings, and they basically form a plaque, which is a cluster of these molecules stuck together, and they clog the brain vessels. So there is no blood flowing in that part of the brain dies out, that little part. That's why it's becoming smaller. So the question is, how can we understand this, at least some form, right? So important thing is in protein is how these guys fall, how they stuck. So we can play around with our tip to understand this, and that was the goal. And in biology, if you go to the Google, you Google it, you will never find the image of the real one, the proteins. Always you will find cartoons with colorful cartoons. So we again use our technique. What you see here, these red lines are amyloid precursor proteins at different length. Of course, some of them are longer because they connect different chains. And this is the drawing of how it looks like. But in reality, it appears straight on our substrate. And we play around again. So in proteins, very important thing is how do they fall. Okay, so here, that's what we did. We use our little tip and we turn it, okay, and we again use this, we twist it. It's like that. Proteins, we twist it. Okay, it's like this, and we fold it again. It's coming in, it's folded, and here it's like that, we fold it. Then you have to show that this is still survive. We have to unfold it. We unfold it, this one. comes back to its normal length. So it's like this. So here's what we did. We turn it to this guy, to this. We twist it, we fold it, we unfold it. This was done by my grad student. She's not here today, but she's about to complete her PhD with this work. So, and my knowledge, this is the first time that a one molecule, a protein, can be played around. But we are not just playing. We can learn a lot from here. How stable these proteins are, how do they communicate, and so on. And so we can provide a very valuable information for medical research for the humankind by using the nanotechnology that we developed. My last part now is for mechanical engineering. Where is Joe? It's gone. Okay, so the student who helped me today was from mechanical engineering. So I want to show you about something about mechanical engineering. How small can you build a machine, right? So, well, here it is. I borrow from the web. This is from San Diego National Lab, and this is not small for us. This is a 50 micrometer, so it's about 50,000 times larger than the scale we used to work. So this is not the real one. So we work on very small machine. Basically, this machine is built of molecules. It's called molecular machine. Okay, I can show you only with this drawing. I just don't have the model to show you. But let me explain it here. We have tripod. Okay, it's like that camera. It's a tripod. That tripod is made of molecules. Okay, and then at the end, we want to put that tripod to stick on the ground. In our case, on the surface. We want to stick it on the gold surface. So we use sulfur atoms here. So sulfur will like a glue. This atom will stick to the gold. Then this will be fixed. We have a rotor, and this has 5 blades. But if you connect the rotating part and the stationary part, you need a ball bearing. So we use a single atom ball bearing called ruthenium atom, and we stick it together, and it looks like this. Okay, so this is the stationary part, this is the rotating part. That's the ball bearing, but single atom ball bearing. So this was designed by the computer and then developed by my colleagues in France, and this was the first kind in the world, that complex machine, man-made, not natural. Where natural machines we have in our body, okay, biological machines. But this is a man-made machine, first time, more complex man-made machine we developed. And so, here they are, the images of the photos. That's I can show you it this way. So what you're looking here, as I put the label 1, 2, 3, 4, 5, is the 5 arms of the rotor. Okay, that's at the low temperature of 5 Kelvin, which is about negative 440. So outside is cold, but not that cold. Negative 440s. Okay, that's the temperature that we work. Here, if you heat it up a little bit, it starts rotating. So you don't see the structure anymore. You see like a rotating. So that's spinning already. Okay, so this. Now, how do we know that that tripod is underneath this? Because we take the image like this from the top. So we can't see underneath. We see only the top part. So we have to first find out whether we have a tripod underneath, which was done by Heath Castle, which my grad student, he loves to destroy. So I asked him to take the duty, and he did it very nicely. So he used the same tip. What he did is he took the image of this, and then he applied the voltage, the same tip, using it. By increasing the voltage, he applied electric field to blow up the top part of the molecule, and he managed to blow up, and it's shown here. And then you see that there is a tripod underneath. So this is how it looks like, the machine. This is not a cartoon. This is the computer-generated image, and it took almost a year to calculate. With the supercomputers we use in Singapore, I have a cross collaboration in cross-Atlantic as well as across the world. And so we did these calculations. And this, of course, little machine, we can also rotate stepwise. Okay, so that's what I will show you. We inject the electrons, we got the signal, we took the image again, we see it's rotated. We can actually control where to go, left or right. If we inject the electron in this area, it will go to the right. At this point, it will go to the left. So I show you here, right, left. Well, this should be clockwise and counterclockwise. So clockwise, more clockwise, going backward, going backward. Okay, we can control which direction to rotate. This was the first time the achievement that we managed to do it, and this is already in several radios and televisions or whatever. But important thing is that we can apply this technique to this kind of small machines, and we can control it. So I will show you with one last movie how it's actually rotate with here. This is how these molecules, little nano machine, rotate. And these calculations took almost a year, I said. This was computer simulated based on our experiment. And this is what we understand. So these are the rotor, these are the tripod. And this is 1 nanometer high, 2 nanometer wide little machines. Okay. And with that, I think I want to end my discussion today. Well, and so what I have shown you today is that we can reach out at the atomic scale using very simple thing called tip, which is a needle I have passed you around to see with a small tip, and that technical scanning tunneling microscope, and not only to image, but to manipulate them. So it's like we are actually reaching out with our hand. Okay, we can control it. So at the atomic scale, and of course, this was done by a group of very brave people. These are my students, and these are current PhD students. These were already former students. They are already they got their PhDs, and these are my undergrad students. They are also, most of them already finished their PhDs. And this is the world's smallest atomic smiley, and thank you for your attention today. With that, I want to use this opportunity to answer any questions, not just the technique I have discussed today, but in general, nanoscience. Please.
With the chlorophyll,
Okay.
what happened when that was changed? What resulted in science?
So,
What could happen?
so this just, it's like a, okay. So the question is, in the chlorophyll that I show you, little chlorophyll molecule, what happened after it's changed? Okay. So I will say you answer in two different senses. Okay. Structural point of view, well, they are stable. It's like you just sitting, and if you stand up, you are the same you. You don't destroy yourself. The same thing, they can go back, they don't destroy. But the electronics properties point of view, they will be slightly different. And we believe, we could not measure it at the time, we believe that also resulted in changes in the color. Basically, the color of the green that we see in the fall time, you see the plant leaves becoming orange and yellow. Of course, these are other molecule causes, like carotene, we also study carotene, or sugar molecules make red colors. But the chlorophyll is probably no longer producing the green light. I mean, let's put it this way. And so the others start take over. Okay? And more questions, please. Please.
Very good presentation. Thanks.
Thank you.
You were showing the single silver atom.
Yes.
To me, it looked like there was a volcano peak.
Fair.
Protons and neutrons, was that the nucleus? And then the electrons you said were the waves? And the way I was taught, I thought the electrons were around the circular nucleus, not a volcano.
So I will repeat the questions. The question is following. when we look at the single atoms, it appears like a volcano peak, okay? It doesn't look like the ball shape that we assume, or I'm just showing the demonstration, right? Well, there are two reasons again. Let me explain it. One is we extended the Z scale more than X and Y. Okay, so in reality, they are more like a pancake in order to see clearly. So what happened is that the atoms are formed by nucleus inside, electrons are surrounding, okay? And if you are on the free space, it should appear as a ball. Or if you have many atoms put together, because of the neighbors, electrons repel each other, it will appear as a ball. But if you are sitting on the top, there is no neighbor, only except the one underneath, so the electrons can travel a little farther away. So it's more of the spread out. So it's more like this shape. It's not like this, no, not like this ball, but it's more like this. So in order to see clearly, we extrapolate Z scale a little more so that you see like this. In real scale, it will be more like a pancake. Okay. It's simply because electrons have little free space to go around. It can't go too far, but it can go spread out a little bit. It's like a water, basically. So electron waves can present around it a little farther away than itself. So it's basically it's a wavelength. That's what you see. But if you bring the next atom, electrons start to repel each other. They start to shrink. Then they start to assume as the ball shape that you think. So the ability to image, not just to manipulate, just to image, give us a lot of learning, because many things that we thought in the cartoons, our assumptions are not correct. Okay, and we learn more deeper. At the same time, many things that we need, we know we can prove it. Please, you first.
Instead of using normal tape, can you coat it with some magnetic coating
Yes.
ceremony and get the spins of your molecules, and can you rotate instead of applying electric field?
So the question is, instead of using normal tip, which is the tungsten tip that we just showed, can you use a magnetic material the tip is made of, and to see the electron spin? Okay, it's a little bit more deeper questions. Only physics students can understand this. Anyway, yes. The key point here is that you can use any materials to make the tip, as long as it's conducting. Okay, so the tip is not just the tungsten. People use platinum, iridium. Some people use gold, and so on. And then if you use a magnetic materials, or coated, or even the bulk tip, chromium, then you can see the spin. I did not show you today, but we did, as you know. We manipulate the spin as well. Not just the atom, but atomic spin can be manipulated.
I
Yes.
also have a similar question about the instrument. So is it okay to ask now?
Yes.
So what are the limitations now you are thinking about this kind of an instrument, and in next decade or in future, what kind of breakthroughs you are expecting?
So he's asking me that what are the limitations of the instrument and what type of things in the future are expecting, right?
Because I see some kind of selection of surfaces kind of specific, as well as when you are dealing with positive atoms and negative atoms, it might be somewhat tricky.
Right, of course, like in any experiments, there are some limitations. We can use only for conducting materials, but there is a new technique. I would just, for general audience, it may be foreign language, new technique called Q plus AFM, which allows the same thing. And I'm building one in Argonne National Lab. I'm planning to build one here if we get that one that we discussed. And so that we at Ohio, we stay at the front line of research. Yes, please. I don't know. Is that a question? Yeah?
Well, you talked about manipulation, so how do you know what force? Is that the same force for every atom, correct, or molecule?
So the question is that we talk about manipulation. How do we know about the force? We can measure the force because we move the atoms. Let me I'm thinking, how can I explain you in a very shortest way? So, I'm sorry. The measurement is, direct measurement can be done with the technique I just mentioned it, the one I'm going to build. But we have already published with the STM how to measure the force. We are the first group in the world, let me say very proudly, to do that, and we succeeded it. So if we are trying to move the atom, just look at it here. This is my atom. I want to move this, okay, here, okay. All right, so I need to come, I had to be overcome. You see, there's some force is required to overcome this. I keep doing it. Oh, I'm sorry, this one's dropped down. We drew it here. It has to be in a certain track, so, okay, so I'm doing it like this. This is actually doing by the STM tip. Exactly like this, what I'm doing now, but in that 1 billion times smaller. Now, how do we know how much force? Okay, I changed the height a little bit now. I cannot move anymore. I'm close a little bit, I cannot move it. I'm touching it, but I can move it. Closer even further, now it starts to move. So, whether it moves or not depends on how close I am. And from the distance of how close I am, I can measure the interactions, and I can use simple vector to measure the vector components of the force, lateral force, how much force I need. It's basically, in the past we called 251. I think it's 2051. In general physics class we use. At the same technique I use, and I measure force at atomic level. Yes, please.
What do your fingers there represent in the real world?
Which one?
Your little balls are atoms.
Okay.
Your fingers there.
This one?
You're having to push over and get to the next spot. What do those represent?
This one or?
Yeah.
These are in the real world atoms of the surface. The question is, what these little bumps represent in the real world?
Different material than the atoms you're pushing?
It could be the same. So in the real world, these are the atoms that made of the surface. The surface, remember, every material is made of atoms. And so if we use a single crystal, the atoms are lined up in a very neat order. Okay. If you cut it off the surface, you see from far it's flat. Closer, you see there's a little corrugation. Each one is one atom. Okay. And then I'm putting as a top, as the atom coming on the top of it. Okay. So that's where it has to overcome the barrier of these atoms. You see that it doesn't go straight. That's why I gave you the sound. I show the sound. I play the sound of the atom movement. It moves discontinuous manner because of this. Okay. Any questions from the student also? Yes, Rox.
What's the force that you can apply to the molecule relative to the bond strengths in the molecule? So in other words, can you apply enough force that you can actually break a molecule?
Yes. The question is, can molecules are formed by the bonds, okay? They put together like a, and if you want to break the molecule, you have to apply a force stronger than that bond, then the molecule will break apart. If you want to move the molecule around, you don't need that much force. So the molecule will not break apart, but if you want to break the molecule, you can apply a strong force either by touching it or by electrons. Well, let me answer this question more detail. So we use the tip I show you with the tungsten tip, this little tip. It's made of tungsten. And if you want to cut the metal, you use tungsten. If you want to cut the iron, or let's say gold, copper, pipes, whatever, you use the tungsten drill, tungsten made of materials. If you want to cut tungsten, you use the diamond saw. That's, everybody knows that, okay, or general rule. So I thought that the tip is made of a tungsten, it's stronger than the molecules like chlorophyll. Because chlorophyll is, we eat the plants. My mistake. It was, I learned it. And so one day I was moving the molecule did not want to move. So I became very upset and angry. And so I became very personal to this molecule. He didn't obey my order. So I want to kill the molecule. So I went in with my tip, just crash it, I just push it down. I can do that, push it. And then I took the image. I was expecting that I have now destroyed the molecule. I want to see my results, my victory. But then I found the molecule was sitting next. My tip was destroyed, so there were a lot of materials coming out of the tip. I was shocked. I tried again, I never succeed. Then I gave up. I went home, thinking what went wrong. Then I realized one thing. The molecules are made of carbons and hydrogen. And remember, diamond is carbon. Diamond is very strong, stronger than tungsten. So the molecules are stronger than the metal that I gave you, the tungsten tip, tungsten drill. You can't kill with that. So why we can eat the molecules? Because the molecules are reactive. If you put a certain environment with water and the temperature, they react. Because of that reaction, they fall apart. But by force, no. So nature has already made a selection. They are very strong. That's my personal experience. Okay. But we can break the molecules basically by means of the electron injection.
If that's true, if you can break a molecule by electron injection, then theoretically, could you do chemical reactions on a single molecule?
Yes.
Have you?
Yes. I'm sorry I did not show you today. It was done 13 years ago for a chemical reaction with one molecule at a time. But I didn't show you today. I don't have it in this computer. Okay. We can do it. Yes. Yes. Any more questions from the student? Yes, please.
Can you, so this is all basic science.
Yes.
So can you give us examples of how this will be applied to actually improve products or commercialize something in the future?
So what I have said, the question is, what is the commercial aspect of this? Or is there anything that we can use for applied sciences? Where the first thing is that this technique, of course, for me, the instrument itself is an engineering feat because we build it, right? We can control that precisely. That is itself is applied. We are using that basically. But now, by using that, we are trying to understand the basic science, basically, because there is a future prospect to be used. I said prospect, not real apply yet, because the devices that we are talking about are becoming smaller and smaller. So there are possibility we are start exploring like single atom devices or single molecule devices. Now, if you want to build a structure with the STM tip like this and make a device, it won't work. I tell you now, because of the speed, forget about it. Okay? If you use, it may be possible, for example, if you use like multiple tip, there exists the technique like 1,000 tips make of chips, and you can move it. But it's very difficult to control of all 1,000 at all 1,000 atom at the same time. So I don't see in that front. What I see is that this technique will be the technique to test your device. So if you build a nano device, a very small device, how can you test? How can you tell that you have the size and it's working? You need to see it. You need to go locally and measure it, the properties. So what I see in engineering aspect is use as an R&D device or to test your device of your the products, basically, at the moment. And of course, there are tip-based nanotechnology, which has been funded by DoD. That is basically we use the tip like 1,000 tips of the chips, make many tips. You make a nano indentation, you crash, and so you at each time you can print nano size little holes. Okay, so thousands of them and so on. Then you can use that as a template to grow things. Of course, those things are much more closer to the reality.
Well, at this point, I just want to thank Dr. Hla again, and if you would like to come up and speak with him or see the demonstration more clearly, please do.
Just come and try here. And if you want to talk, I'm still here. So